Hi, this is Mr. Mack. This is a video that's basically going to talk about derivatives, or the derivative, okay? Now, to start off with, we consider ourselves to have some kind of a function, call it f of x. And then we have perhaps some point A on the independent axis, and the y value of that point would be f of a. That would be this distance here. And what we would like to know is the slope of the line that's tangent to that curve at that particular point. Let me just see if I can get this. Pretty close. Okay, now what we're dealing with here is a way to do that, because in algebra we learned that to find a slope, it was the you needed 2 points, and you took the change in y and divided by the change in x. In other words, y2 minus y1 was how much y changed from point 1 to point 2, and x2 minus x1 was how much x changed from point 2 to point 1. And the ratio of the change in y, the dependent variable, to the change in x, we defined to be the slope. Now, it was possible to do that in algebra because we were dealing with lines, and the slope is a constant. Once we get past lines, when we get to curves, we'd still like to know what the slope is, because the slope, or the instantaneous slope, the slope of the tangent to the curve at a particular point, is a measure of, at that instance, how fast the dependent variable is changing with respect to the independent variable. Now, the way we get at this is we say, all right, we're going to say that some distance past A, we'll call it h units, we'll take a look at another point on the curve. Now, this point past A is actually A plus h, if h is the distance between the two. And then the height of the curve at this particular point is f of a plus h. And so if you wouldn't mind, I'm going to tell you that this point right here has coordinates a, f of a, and this point has coordinates a plus h, comma, f of a plus h. Now, a line that goes through those 2 points we refer to as a secant line. The idea in geometry was a secant was a line that intersects a circle in 2 points, and we use that same terminology when we talk about a secant line on a curve. Now, the slope of this secant line is equal to y2, which is going to be f of a plus h, minus y1, f of a, over x2, a plus h, minus x1, which is a. And this simplifies a little bit. We end up with the slope of the secant is equal to f of a plus h minus f of a all over h. Now, the thing that happens is, if we allow this second point, let me just draw an arrow here and I can point to it for you. If we allow this second point to move along this curve towards the first point, the secant line will more closely resemble the tangent line. See, if we so as the secant line, as the point comes towards the first point, the secant line gets closer and closer to the tangent line. So what we say is that, or what we define is, we're going to say the slope of the tangent line, we're going to let that be equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Now, notice that expression, this expression right here, is the expression for the slope using the 2 points along the curve f of x. Unfortunately, when the second point slams into the first, when we actually have a tangent, when there's only one point of intersection, the line doesn't exist because it takes two lines. It takes 2 points to determine a line. So we use the concept that we've developed of limits, where we're going to look at what it's squeezing in on, but not actually look at the value. So we define the slope of the tangent to be the limit, and that's why this part is here. Now, this turns out to be the derivative. Because it is a function derived from some function, f, and the definition of the slope of the tangent line. We use symbols like f prime of x, and we say that this is going to be equal to the limit as h approaches 0 of f of a plus h minus f of a over h. Now, it's pretty easy to see that if you were to do direct substitution in evaluating this limit, you would get 0 over 0. So this is an indeterminate form, and there is a way actually to evaluate this in many cases. And so what we're doing is we're going to make the derivative be, we're going to define the derivative to be this value. And so it is a limit. And that's where we're going to go with that. Now, let's talk about a concrete example where you can see this a little bit. Okay, first of all, imagine we have a function. The input variable is time, and the output variable is a point's displacement from some particular place. And so let's say we have this function s of t. At this value of t, the point is this far away from the origin. Well, let's use a here again. And at some time later, h units later, this point then would be a plus h. The point is this far away from the starting point. Now, remember, average velocity is equal to the total distance divided by the total time it takes an object to move from one place to another. So if you look at these 2 points and the secant line that contains those 2 points, this line segment right here represents the change in displacement and this line segment right here represents the change in time. And so the change in displacement, the total distance the object has traveled from time a to time a plus h, divided by the total time, h units, which is the change in time, is the average velocity. So it should be clear to you that the average velocity is really the slope of the secant line between the 2 points on the displacement function. And as these values get closer and closer together, as h gets smaller and smaller, as these 2 points get closer together, that average velocity becomes to look more and more like the instantaneous velocity. So the instantaneous velocity at point A turns out to be the limit as h approaches 0 of s of a plus h minus s of a over h, which is exactly the same thing. So what we draw from that is that the instantaneous velocity is the derivative of the slope. Now, because of the definition of the derivative, we can find the derived function for some functions, and we're going to spend a lot of time learning more about how to find the derived values of the derived values for the derivative from different functions. Let's just take a look at a simple one right now. Let's say we have f of x is equal to x cubed plus 2. I can do a better job on that cubed, I think. Hang on here just a minute. F of x is equal to x cubed plus 2. And let's say we want to find the derived function for this particular function. Now, the derived function is called the derivative, and a lot of times the symbol is f prime of x. We have some other symbols. I'm not sure. Maybe they're spoken of in the book at this particular section or the next section. You should actually look at the book too to find those. And we'll be talking about them from time to time. But now, we're told by the definition that the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, you all have so much experience with functional notation that I would kind of expect that you would understand how to substitute this in. F of x plus h, let me just write this. F of x plus h is, pause. Now, see, f of x, let's see, make another arrow here. F of x says when you have an input, cube that input and add 2. Now, f of x plus h is saying the input is x plus h. So what we get is the cube of that input plus 2. So the next line is going to be f prime of x is equal to the limit as h approaches 0 of x plus h cubed minus x cubed, x plus h cubed minus 2. I could do this. Why am I having so much trouble? Minus 2, see, because it's x cubed, plus 2, minus, and then in parentheses, x cubed plus 2, all over h. Obviously, if you put h in for the numerator, you get x cubed, and then minus an x cubed, that's 0. 2 minus 2, that's 0. 0 on the top, 0 on the bottom. So more evaluation is necessary. Now, here's what we do. Don't drop this limit as h approaches 0 until you actually substitute the 0 in for h. When you're showing this, this little part must remain. Now, x plus h cubed. You learned in Algebra 2 the pattern for cubing a binomial. A plus b cubed turned out to be a cubed plus 3a squared b plus 3ab squared plus b cubed. So you should be able to just write this as x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2 minus x squared, minus x cubed, excuse me, minus x cubed plus minus 2. Distribute that minus sign. Minus 2 all over h. Now, if you look at this a little bit, x cubed minus x cubed is 0. 2 minus 2 is 0. So what we have now, let's just make this smaller. Put it someplace else. Okay. What we have now is the limit as h approaches 0, and I'm going to take some liberties here. See, I've got 3 terms left in the numerator. Do you notice that there's an h as a factor in all 3 of those? So I'm going to, if you'll excuse this horrible expression, get the h out of there. 3x squared plus 3xh plus h squared. And on the bottom, I have the h. Now here is the 0 over 0. So I can cancel that out since I'm taking the limit. And then I do direct substitute, and I get 3x times 0. I'm sorry. What am I thinking? 3x squared plus 3x times 0 plus 0 squared, which turns out to be just 3x squared. So the derived function for x cubed plus 2 is 3x squared. Now, you're going to get a chance to do a lot of derivatives, and before too very long, we're going to give you some rules so that you can know how to get those derivatives much quicker than evaluating the limit each time. But if it says to you, or if the directions say, use the definition of the derivative to find f prime of x, or find the derivative of this particular function, then you have to set it up using the definition, which is right here, and then you have to evaluate that limit to show that that's the derivative. After we do that for a section or two, it probably won't be necessary for you to do it a lot anymore, but it is important that you know what it is that you're doing. And it is also important that you know when you take the derivative, you're getting another function, and this function tells you the slope of the tangent line to the curve at any point x. And we're done.